Most of us already have small, microscopic clusters of cancer cells in our bodies. In their initial state, they are completely isolated. Without a dedicated blood supply, they can't grow past the size of a pinhead, and they remain relatively harmless to the broader body. To become a deadly, growing tumor, that cluster has to overcome two massive biological hurdles. First, it has to evade the body's built-in mechanism for programmed cell death. Second, it must force the creation of an entirely new blood supply to feed itself, a process known as angiogenesis. A dormant cluster cannot accomplish this in isolation. The cancer cells must actively manufacture and broadcast chemical signals to trick the surrounding healthy tissues into assisting their growth. A tumor's survival is dependent on its ability to build and pump out these manipulative chemical distress signals. Without them, it starves. To build those signals, cancer relies on a highly specific raw material. It uses a molecule called arachidonic acid, or AA. Arachidonic acid is a polyunsaturated omega-6 fatty acid. In normal human biology, it is naturally stored within our cellular membranes, waiting to be used for basic cellular functions and localized immune responses. Malignant cells hoard this material on a massive scale. Look at this comparison of a cell membrane's lipid composition. While a healthy cell maintains a balanced reserve, the membrane of a human lung cancer cell swells to 40% pure arachidonic acid. This massive stockpile serves as a high-density fuel reserve for the production of weaponized chemical signals. The transition from a harmless cellular cluster into a metastatic threat requires the aggressive accumulation of this specific dietary fat. Having hoarded the fuel, the cancer cells now need a way to process it. They achieve this by synthesizing excessive levels of specific processing enzymes. The primary driver of this process is an enzyme called COX-2. COX-2 acts like a dedicated biological refinery. It physically binds to the cell membrane and rips the stored arachidonic acid out of the wall, rapidly processing it into a new shape. The chemical output of this processing is a class of highly inflammatory molecules known as eicosanoids, with one of the most prominent being PGE2. The cancer cells continuously pump these freshly manufactured inflammatory molecules outward, saturating the local environment. A progressing tumor acts as a highly active chemical factory operating inside the body, altering its surroundings to ensure its own survival. Once released, these arachidonic acid derivatives go to work on three fronts. First, they act as potent survival factors, aggressively forcing the cancer cells to multiply while disabling the biological triggers for cell death. Second, they solve the tumor's starvation problem. The eicosanoids promote the release of growth factors that force nearby capillaries to sprout new blood vessels, piping nutrients directly into the mass. Finally, they pave the way for the cancer to spread. The resulting wave of local inflammation loosens the structural integrity of the surrounding tissue, allowing individual cancer cells to detach and begin migrating. When these migrating cells reach distant capillaries, these specific eicosanoids act like molecular glue, helping the rogue cells stick firmly to the vessel walls so they can implant and start the cycle over. The conversion of arachidonic acid into eicosanoids provides the critical signaling required for the tumor to grow, feed itself, and spread. This biochemical dependency provides a clear target. If arachidonic acid metabolites are the primary chemical fuel, disrupting that specific supply chain can cripple the tumor. This is the mechanism behind pharmacological treatments known as arachidonic acid cascade inhibitors, specifically COX-2 inhibitors. This text outlines their precise function. These drugs seek out the COX-2 enzymes and chemically block them. By binding directly to the biological factory, they physically prevent the enzyme from turning the stored fatty acid into pro-tumor signals. Blocking this pathway is a documented, clinical method used to choke off angiogenesis and stall tumor progression. There is also a secondary, nutritional intervention that targets this exact same biochemical pathway, omega-3 fatty acids. Omega-3s share the exact same enzymatic processing pathways as omega-6s and arachidonic acid. They both require the same COX-2 biological factory to be metabolized. Omega-3s physically compete with arachidonic acid for COX-2 enzymes, acting as a biochemical Y-junction that jams the factory doors. This blocks the pathway, suppressing dangerous inflammatory signals. While arachidonic acid promotes tumor expansion, An influx of omega-3s pushes starved malignant cells towards self-destruction. Identifying and disrupting this specific biochemical supply chain allows us to directly target the pathways tumors rely on to advance.